Today we're going to look at exponential functions. An exponential function is a function in the form y equals ab to the x. Now, a couple of restrictions here. A can't be 0 because otherwise it's just going to say y equals 0, and that would be a horizontal line or a linear function. And b cannot be 1. Because again, that would create a horizontal line. It would just be y equals a. And I'm also going to say b has to be greater than 0. Okay, b can't be negative because, and it also can't be 0, but it can't be negative because if I had like a negative 2 to the x, what's going to end up happening is you'll have something that's like up here and then down here and then up here and then down there, and you're not going to get a nice continuous function. It'd be a discrete graph. So when b is greater than 1, it is called a growth factor. And you can see this y equals 2 to the x. We've got 1, 2. You can make an input-output table if you want. If you want to do that, you do like negative 3, negative 2, negative 1, 0, 1, 2, 3. It's 1, 2, 4, 8, and 1/2, 1/4, 1/8. 2, 4, 8, 1/2, 1/4, 1/8. This part's going to keep on going up forever. This part's going to approach 0 but not get there. So our domain here is all real numbers, and my range is y is greater than 0. It's strictly greater than 0, not greater than or equal to, because it never reaches 0. When b is between 0 and 1, we call that a decay factor. Similar kind of graph here. And have 1/2, 1/4, 1/8, and then this is going to be 2, 4, and 8. You can see that decay, how it's getting smaller and smaller and smaller. You actually still have the same domain and range as the last one. The two graphs look really similar. The only difference is they're actually reflected over the y-axis between them, two of them. Now, when I have something like this with this 2 times 3 to the x, what I have here is a parent function of 3 to the x with a vertical stretch here of 2. So my parent function of 3 to the x is going to look like x 3 to the x. I'm only doing 2 because 3 is going to be 27 and it'll be off my graph for all of this. Okay. And then when I stretch this, I'm going to do a vertical stretch. I'm going to double all of these y values. I'm not even going to double the 27 to 54. It's too big for my graph. Okay. So instead of being at 1 here, I'll be at 2. And then this next one's going to be up at 6. Next one's going to be 18. It's going to be pretty high off of my graph. 2/3, 2/9, real small. Kind of like that. You can see the domain is still all real numbers, and my range is still greater than 0. The only time my range is going to change is if I have a vertical translation up or down. That'll change this as y is greater than or what. A number or y is less than a number. Also, a reflection over the x-axis could flip it the other way. Find an exponential function with f of 0 is equal to 5 and f of 2 is equal to 20. Then find f of 6. So what I have here is 2 coordinate points, 0, 5 and 2, 20. What I'll do is I'll use my exponential function format. That's at y equals ab to the x. We're going to assume here that it doesn't have a horizontal translation or a vertical translation, but know that we could write different ones if I included those in as well. So y equals ab to the x. I'm going to use this coordinate point and say 5 equals ab to the 0. I'll also use that same format and say, okay, 20 is equal to AB squared. Now, b to the 0 is 1, so this is really 5 equals 1a. Oh, so a is 5. Then I'm going to take that value for a and substitute it in here. Divide by 5. B squared is 4. So b is either positive or negative 2. But we know from the rules of exponential functions that b can't be negative. So we're going to say y equals 5 times 2 to the x. If b was negative, then you'd see that ping pong back and forth between positive and negative and not get a nice continuous function. Take a moment and try this one, finding an exponential function that goes through these points. It's a little trickier than the last one. Alright, hopefully you had a chance to pause the video and try this one. So when I take the point 2, 2 and 3, 4, I'm going to do 2 equals AB squared and 4 equals AB to the third. Now this one's not as easy because I don't have B to the 0 happening where it eliminates it. So what I'm going to do instead is I'm going to solve this one for A. You could solve for either variable, but I like to solve for A. I find it's easier. And then I'm going to take this and plug in for the A here. I also like to solve for the one with the smaller power so that I end up with B on the top. So what I have here is 4 2b cubed over b squared. I'm going to use my rules of exponents to say that's going to be just 2b. And then b is equal to 2. Well, if b is equal to 2, a is equal to 2 over 2 squared, it'll be 1/2. So my equation is y equals 1/2 to the x, which is not the same as just like 1 to the x, because we'd have to do that exponent first. Half-life is the amount of time it takes for half of the material to decay. You can do this a couple of different ways. I happen to like using the half-life formula. Half-life formula looks like A equals P 1/2 to the time over half-life. Some people use H or K to represent half-life. I usually just write the words half-life. A radioactive isotope has a half-life of 10 days. It starts out at 750 kilograms. How much of the isotope is left after 5 days, 15 days, and 20 days? So we're going to have start, so P is equal to 750. The half-life is 10. Okay, so for my 5 days, I'm going to have 750 1/2 to the 5 over 10, which will be 1/2 as well. For the 15 days, I'm going to have 750 times 1/2 to the 15 over 10. 20 days, 750 times 1/2 to the 20 over 10. $750. Oh. Five to the 0.5. 5 over 10 to 0.5. 530.33 kilograms. Still quite a bit. 150.5 to 1.5. You could also do 15 divided by 10. Just make sure you put it in parentheses. 265. 17. And last but not least, this one I'm just going to do 750 times 1/4, because 1/2 squared is 1/4. 187.5. Okay. So, a radioactive isotope has a half-life of 6 days. What is the daily isotope decay? I want to know what percent does it decay each day. So if I start at 1 for one whole amount and say 1/2 to the 1 over 6, 1 because I'm looking for daily, how much is being reduced in one day. 0.5 to the 1/6, which is really just going to basically take the 6th root of it. True story. 0.89. So 11% has decayed. Roughly. Yeah. 10.9 if you wanted to be more precise. And that concludes this lesson.